so how can I represent it to compute this term? So in fact, this term can be represented as 1/2. So h is a vector that represents displacement in parameter space. So we'll take transpose of this vector time the Hessian time h. And in 2 dimensions, I will have h1, h2. It's the displacement of parameter 1, parameter 2. Here I have my second derivative. So it's the second derivative is the derivative of the derivative. It's an acceleration. I'm looking at the rate of change of the derivative when I move in the parameter space. And so I have, and one property is that this matrix is symmetry. And I will multiply it by this, by h1 and h2. So the gradient of it is the Hessian times h, and the Hessian of this function is the Hessian of f. That's why I can use this quadratic approximation to study the behavior of an optimizer in this region. Because the curvature represented by the Hessian is the same than my original function here. Okay, so for now, we will just optimize over quadratic function to just study what kind of problems we can have when we are not very far from a local optimum, and but still what kind of problem we can have for training deep learning around these in this area. So I can define different quadratic function by defining h. Here I take the identity, and you can see that it's a perfect ball. If I move in one direction, if I move by 1 in one direction, the loss will increase by 1, and if I move by 1 in the other direction, the loss will increase by 1. It's isotropic. All the parameters have the same impact on the output. Now if I use 4 for this component and 1 on this component, then if I move for the parameter on the x-axis, the loss is moving much faster. And if I move on the y-axis, the loss is moving slower. So parameter 1 have a stronger effect on the output than parameter 2. And with h, I can also do some rotation. So now the axis of my loss function are not perfectly aligned with the parameter space, with the axis of the parameter space. And it can be also difficult to optimize. So I can generate different kind of quadratic function by just specifying this matrix H, and it represents different Hessians that I can obtain here. It's like I'm fixing H, which represent this quantity, and it's like I'm creating new functions here that I want to study. I can also create other functions that are more difficult. They are saddle point functions. So here I will use for one direction, if I increase the parameter, the loss will increase. And if I increase the second parameter, the loss will decrease. So they have different effect on the loss. And you can see why we are calling a saddle point a saddle point. The saddle point is at the middle here, which is represented here. And if I go on this axis, the loss will increase. If I go on this axis, the loss will decrease. And I can generate the loss for any point in this space, and I create a saddle shape. That's why we call it saddle point. Here I can create other one. I can even rescale and have different shape of saddle. Okay, so before creating our first optimizer, we will just review what is an optimization algorithm for deep learning. So first, I will have this algorithm here, the optimizer. The optimizer will propose some parameters, will fix the values of the computational graph. The model will receive the parameters, do one forward, evaluate the loss function on all the examples, take the average, and then we'll do backpropagation in the model. And I will retrieve all the gradients for all the parameters as a vector, and I will give this vector gradient, to my optimizer and the loss. So first, why gradient is so important in optimization? So remember, we have this linear approximation. Now I move the term f of a on the left of the approximation equal. And so the difference here between the loss evaluated at parameter a, and I do a little step, and I go to parameter a plus h. If I take the difference with the loss at the initial parameter, this difference will be approximately given by the scalar product between the gradient and h. And we can ask the question, what is the best h that will minimize this quantity? I want to go to a loss of equals 0 as fast as possible. So I want to minimize this, this quantity. This term will be smaller than this term, because every time I do a step, I want the loss to decrease. And I want to minimize it. So what is the h? What is the direction that will minimize this quantity? Or where I will have the biggest improvement on my model. So it's another optimization problem, but it's a very simple one. Here I minimize over all possible direction. So I'm at one parameter. I fix my parameters. I look at all possible direction around me. All the direction, I will fix their length to be equal to 1. Because I just want to find the direction. I don't care about the length of the displacement. And so I want to find the minimum displacement that will minimize this quantity, which approximate the improvement of my model. And the definition of the scalar product is the norm of the gradient evaluated at A times the norm of H times the cosine of the angle between the two vectors. So the vector associated to the gradient and the vector associated to the displacement. This is equal to 1 because I fix it here. The norm of my displacement is equal to 1. This does not depend on H at all. It's only the gradient of f evaluated at A. So I can replace it by C. And now I must find the H that will minimize the value of the cosine of the angle. And to minimize the cosine will be minimum if I go at the opposite direction of the first vector. So the first vector is the gradient. Here I have cosine of 0, which is equal to 1. And if I go on the opposite direction, I have the minimum value. So the gradient tells me the direction where I will have the biggest improvement in minimizing my error. And that's why it's a very interesting quantity. So it will give me the steepest slope in which I should move to minimize the loss the most rapidly. But the gradient is a local information. It has been defined only at one given point. And since it's a linear approximation, we don't know how the error will accumulate if h is too big. But at least we have the steepest slope. And it's a little bit impressive because if you think about it, if I'm in two-dimensional space, to find the steepest slope, I must try really everywhere around me. I must do I must check a lot of different directions to find the steepest slope. But here, the gradient, I just need to do two tests, one in one axis and one in the other axis, and that's it. With this information that I've just retrieved, I can use the gradient as my steepest direction. So to find the steepest direction, I only need information which is similar to the number of parameters. I don't need to do more tests than this.